Hi, everyone. Thank you for being here, for choosing this room for your lunch. So my name is Benoit Takat. I'm a researcher at Yukon U Research Center in the field of hydrology. I'm pleased to introduce Dr. Paul Villard from Geomorphics and adjunct professor at Guelph University. Dr. Villard is an expert in coastal and fluvial geomorphology, sediment transport, and stream restoration. He has 30 years of experience in research and 20 years of experience in consulting. His expertise represents a fascinating field of geoscience to me, and I hope that it will generate conversations among the participants here. So, Dr. Villard, the stage is yours. Thank you.
First, I want to thank the Yukon Science Institute, the Yukon University, and Yukon GeoScience Forum for allowing me to present. If I appear to be a little bit surprised, is because this is not what I had originally planned. I've been working and have been in discussions with Benoit at Yukon University and Corinne Smith, who works with me at Geomorphics, on starting some research projects. We were talking about doing hydraulics under ice, talking about geomorphology and its impact on ice formation, looking at sediment transport, and also about bioengineering and natural channel design and its applicability in northern climates. I had anticipated to be talking to 5 to 10 academics and students. This is a slightly larger venue than that, but I think I can still provide some value. There was a little bit of concern. You come to a conference, you're always a little concerned that maybe your topic will be off topic, it won't be well received. But this morning calmed my nerves on that. There were some great talks on cryo purification of water using biomimicry. There were talks about bioengineering, biocrusts, and using lichens for stabilizing the ground, using wattles for dealing with head cutting and permafrost. So there was the range of really good talks, and that introduction of bioengineering into the northern climes and addressing erosion problems through its applications appears to already be taking root. I also had the opportunity to listen to Pierre Lasson's keynote speech on Sunday. It was great. I have a new respect and urge to purchase gold. But he also brought up a really important point that really struck home with me, which was this idea that everywhere you go, people are different, but we're all the same. I have a similar concept with regards to rivers. What I mean by that is there is a diversity of rivers across a number of different geomorphological landscapes, across different biomes and climatic conditions. But if you have the same sediment supply, the same hydraulics, similar vegetation communities, you will end up with a similar morphology. What that means from a management perspective is things that are done in other areas may, notice I said may be applicable in other areas too. The mistake is forgetting that there are differences. That is where the mistake comes, and that's where the idea of research in this topic comes to the forefront, is that idea of these ideas like bioengineering may be really effective here, but they'll likely need to be modified. They'll have to be site-specific solutions, and that's where that concept of the research comes in. I've been doing, as Benoit noted, I've been doing research and consulting for 30 years. I've had the opportunity to work in New Zealand, British Columbia, across a range of environments, California, a lot of work in Ontario, and even one project in Belize, which taught me a lot about systems that are controlled by hurricane conditions. So what that taught me is that you really have to make sure that whatever you're working on is site-specific, but you can transfer knowledge from one area. You can share that information, modify it, and then effectively use it in your own jurisdiction. So the overview of the talk is I'll give an introduction to bioengineering, definitions and history. It is not the new kid on the block. Bioengineering has been done for a very long time. I'll talk about bioengineering experience in the South provinces, mostly in Ontario, where I have a lot of examples. Then I'll talk about northern climates and bioengineering, and then pros, cons, opportunities, and potential design adjustments. There'll be a little arm waving in there. And the reason is this talk was originally about what kind of research could we do? What could be the differences between the South and the North when we bring these new techniques or these techniques into a new jurisdiction? Bioengineering is a tried and true method. What I mean by that is the use of vegetation and inert materials like rock and wood have been used for a long time for stabilizing. Bioengineering is actually a very effective method of erosion control. In a lot of cases, riprap or large rock is used. It's placed on the banks, and we hydraulically size it and put a factor of safety on that. What we're hoping with that is that that rock will not be lifted, scoured by ice, taken by hydraulic characteristics, but the entire strength of the bioengineering comes from the mass of the rock. Once you introduce vegetation in, growing material, it can bind, producing almost what you would find like a metal gabion basket, but it's a living structure that binds into the banks and actually provides more strength in the long run than the stone or the wood would provide by itself. It's also about soil development and that creation of soil and that binding mechanism to create more of a structure versus an individual particle. So it's been around a long time. First records of it are 2000 BC in China. In 100 BC, there are records of fascines or wattles being used in Europe. 28 BC, there were willow bundles drawn onto tapestries, which I guess was the first detail. That's a good engineering joke. Anyways, when we move into the 1600s and we look at a more Eurocentric view, there's an increased prevalence of the use of vegetation for erosion control, for riverbanks, for basically channelization, bank stabilization, and a lot of gully control. The drawing that you're seeing at the bottom is from the 1730s. It's one of the first guidance documents on applying bioengineering, and in this case, wattle treatments in Europe for erosion control. It is not the new kid on the block. I like that little. Anyways, now we look at the more recent history. So why do people think that bioengineering is a new concept? And the reason is that after the 1940s, we had access to a lot of labor, fossil fuels, and concrete. And in a lot of urban centers, cement and engineered solutions were applied to basically address erosion concerns and to get the water off the landscape quickly. It was very effective for moving water. It did have other unanticipated impacts, erosion downstream, impacts to aquatic ecology. There are a number of things that we lost in that trade-off of being able to move the water off the landscape quickly. Come to the 90s, we start seeing in a lot of urban centers across Canada, I'm talking particularly in the Ontario context, that we needed a new approach if we wanted to maintain the ecology and we provide other functions other than moving water off the landscape. So we have this resurgence of bioengineering in the 1990s. I was lucky. My career in consulting started in the late 90s, which means I was able to be involved with this process of trying to build new concepts and bring them into our way of managing rivers. 1990s, the emergence of natural channel design, the idea of taking geomorphological forms that we find on the landscape and replicating them in the design. 1996 was the first comprehensive guide for bioengineering. So there's a lot of documents already out there. There are specifications, there are hydraulic sizing reports, there are a lot of material for using bioengineering. Terms like biomimicry in the late 90s came out, which is basically just taking surrogates from nature and using them for restoration. And then nature-based solutions, a concept that we're hearing more and more about, which is actually looking at the ecological, social, and the the other benefits that these kind of bioengineering projects provide. So it's not that bioengineering is not being done in the Yukon. It is. We have the Yukon Revegetation Manual from Yukon University. Minto Mines, Yukon University has been working with there for mine revegetation and reclamation. There's others too. I only put a short list. There are many others. Faro Mine with EDI. Kolomak Mine in the Northwest Territories looked at bank protection. That Hewitt paper is online. It's available online and it's quite good. Urban ecological restoration, which is more what I've done quite a bit of. The use of native species to stabilize clay cliffs in downtown Whitehorse. That's been work that was done in 2015 by Yukon University. And then there's also been an EDI study looking at the use of bioengineering for shoreline in riverbank erosion protection. So the concepts are coming in. What I'd love to see, and I've been able to watch this process occur in Ontario and other jurisdictions, is bioengineering does not remain a unique tool that's only used for habitat restoration, but it becomes a larger portion of the toolbox that engineers, biologists, geomorphologists use to deal with river management. And recognizing that it can be used as part of that overall toolbox for both protecting, doing erosion protection, and also for providing the ecological benefits. Why bioengineering in the Yukon? First, it can be used for a whole bunch of different situations. Shoreline protection, riverbank stabilization, so real true erosion protection, stream diversions at mine sites, tailing pond stabilization, support for bioremediation at contaminated sites. There should be an asterisk there. There's a lot of management and other things that have to go on with regards to that. It's not simply about planting vegetation. Natural sediment traps, increased resilience to seasonal flooding, increased resistance to erosion from ice. And that's an important topic for the Yukon in that ice is a dominant process in your rivers. It doesn't mean it's not occurring in other locations, and I'll give examples, but it is a dominant process and it will need to be better understood how it interacts with bioengineering. And promoting overall sustainability. Bioengineering is green, but not soft. I actually heard a question this morning that I've heard many times in other jurisdictions, an engineer asking if there were specs, hydraulic sizing, because at the end of the day, when something is put on a drawing, you have to be sure that it works. I can comfortably argue that bioengineering provides erosion protection. You can hydraulically size materials, you can use large wood, the vegetation simply provides additional benefit. Beyond the protection against erosion, what other benefits does it provide? Well, shading, it reduces warming, which is a concern in a number of the provinces, increased carbon storage. I'm currently working through Geomorphics, which has been around for 10 years, on about 90 kilometers of river restoration design. And in the last 10 years, 30 kilometers of that has been installed. And these are small streams, but very large floodplains. The carbon sequestering associated with that work, particularly in greenfields, is substantive. Not that that would be a reason for doing it in the Yukon, but to recognize in other jurisdictions, it's an important component with dealing with climate change is an important fact to know. Increased large organic material inputs, increased habitat and biodiversity, improved water quality, and enhanced ground permeability, infiltration, and groundwater exchange. The reason I put that one up is that often when we put in engineered structures, a concrete retaining wall, armor stone, or some treatment like that, we actually stop that interaction on the groundwater between the channel and the floodplain. While with bioengineering, because there's soil involved and it's more porous treatment, that hydrologic connection can continue. Also, reduced phosphorus inputs. Again, may not be a concern in the Yukon, but in a number of the jurisdictions I work in, we have eutrophication in wetlands. We have the Great Lakes where both nitrogen and phosphorus inputs are problematic. having a method for minimizing those inputs or offsetting is quite important. I don't completely agree with this chart before I show it to you. It was done by Copen and Richards in the 1990s, and it basically talks about the relationship between bioengineering and more engineered structures and the whole period in which we design, install, monitor, and then have to replace and go through that process. Along here, we have the solid line is basically a traditional engineered approach, a wall. You investigate and design, you do the construction, and then basically there's a period of monitoring, and then walls don't tend to fail gracefully. So what happens is at some point the wall is compromised and you have to go through the whole design reinstall process. I actually think these costs initially, the bioengineering and the wall, are probably quite similar. I don't completely agree with Copen and Richards, but I do agree that with bioengineering, you can go out because the features tend to fail gracefully. And what I mean by that is they settle, they adjust, vegetation will be removed, but new vegetation occupies those spaces where the vegetation's been removed, that it actually takes less inputs to basically maintain that infrastructure versus a hardened engineered feature. So over the long run, you may get cost savings. I say may get cost savings. So there'd be some discussion of, well, why would you then want to do this over an engineered approach if the costs are going to be similar? Because of all the other environmental benefits you gain from using bioengineering over some of the more traditional gabion baskets, armor stone, or concrete walls. This is to show you that in a number of provinces, we have very similar conditions to the Yukon. I have used the territorial flag and the provincial flag just to point out where the photos are from, but I'm figuring from this landscape, you all could have guessed. Same issues, undercutting of the roots, scour, ice scour, major events, basically creating erosion, and even in some cases, some geotechnical failures. The processes are the same. The morphologies in many cases are similar. It's just the magnitude of the different processes, ice, hydraulics, growing season, that's what actually varies. I will also point out that Horse Creek is much prettier than this creek that from Mississauga. I don't think you guys realize as a geomorphologist, the ability to give a talk right next to the Yukon River is, in many cases, a dream come true. Anyways, one of the things about bioengineering is it creates a resilient structure by creating roots and putting wood mass in front of the structure. Even if damaged or removed, the vegetation can often reestablish itself and it will self-heal. Even when compromised, structures fail gradually rather than catastrophically. That's that fail gracefully term. Hydraulic benefits, additional roughness. Armor stone walls, concrete walls, very low roughness. Soon as you put in the wood material, you're actually forcing the shear away from the bank. So from an engineering or physics perspective, it provides for a more resilient wall. Resistance to high shears and velocities, reduce through flow and surface erosion. The one problem or thing that you have to recognize is when you initially install it, you're completely relying on the strength or the mass of the rock because it takes a while for the material to grow. And in the Yukon, where the growing season is shorter, that may mean that you're not looking at 1 to 2 years or 2 to 3 years, but 3 to 4 years for that to fully establish. We don't completely know yet because no one's been digging into any bioengineering to look at see how quickly the root structures are developing, which was one of the research questions I was talking to Benoit about. This is a treatment on Lake Ontario in Oakville. We can see the rock structures in front buried pretty deep. Then a new beach is installed in front of it, and plant material are being installed at the top and along a number of the lifts where it's exposed to wave attack. The initial strength comes from the weight of the material. It's basically the mass of the material. Later on, once the roots establish and tie into the native material or parent material, it provides additional strength. For those people working in wave environments, you also know that there's pressure differentials that tend to suck material out. In a lot of cases, filter cloth would be applied to the back to reduce that kind of suction effect. But once you have vegetation in place, it basically creates a filter that stops the fines from being moved and migrated through. If we look at a bank treatment in a river, we have the exact same system. We have the mass of the material initially, then basically we have the roots tying into the banks. And I know for many who don't work with plant materials, there's this concept that it really can't be adding that much strength. If you have a properly bioengineered bank treatment, the erosion, the velocities to scour it can be in excess of 3 meters per second. Okay? Even grasses can take sustained velocities of about 1.5 meters per second. So the vegetation does provide a substantial benefit for the overall strength of the treatment. Then again, how quickly does it grow? How well does it establish? Will you get that same effect if you try to apply it in the north? So this is one treatment. I usually don't design this way. You can see a very narrow channel here. It's in an urban center. It's in the middle of a cemetery. The channel cannot migrate for obvious reasons. We usually would have involved some level of natural channel design too. And what I mean by that, we would have provided some sinuosity. We would have provided some terracing, some other ways of dealing with the hydraulic energy. But in this case, we can't simply because of the constraints. This was constructed in 2022. It's in an area of Richmond Hill, which is outside of the Greater Toronto area, a little bit north. In that period, basically with our growth rates, we can get 4 centimeters a day of growth through the growing season, up to 30 centimeters a year in controlled conditions. We have been to sites after 2 years where the willows have grown 2.5 meters, so substantially larger than that. The root matrix, because I went and dug in, this rock did not come out naturally. I did pull it out to look at the root structure right down here. When we installed it, this was not bare root material. It was live stakes. It was a piece of wood with no roots. When I went back 2.5 years later, 35 centimeters of root production. What's interesting is there was only 15 centimeters of soil. So it's already tying into the materials behind it. Will that same process occur in the north? Something to be studied or looked at. So bioengineering can take on a range of types. There are hundreds of details for bioengineering, and there's all the way from soft treatments that are used in low energy environments to more substantive treatments that include wood, rocks, erosion control mat, compost, and even in some cases, soil enhancements to improve the growth rate. But the most simplified one is basically taking a stake 1 meter long, cutting it off during dormant season, which in the Yukon is more extensive than other places, so you have a longer period to collect the materials, and then basically hammering it into the ground and allowing it to grow. Put a reasonably high density of them, and it will actually provide a substantial amount of protection. Wattles, there was a talk this morning on wattles. It was great. Just want to point that out. Wattles are just bundles of either dogwood, willows, alders. They're basically tied together. In this case, it is buried under the soil and then covered with erosion control mat. This is on Mohawk First Nation lands in Montreal. It is in an embayment on the St. Lawrence River. Why is that important? This is a reasonably low energy environment. So this softer treatment will be very effective dealing with erosion location without the addition of stone or without the addition of additional wood material. Brush mattressing. Brush mattressing is basically building a bed. You lay out a brushing, you bury it, dormant materials again, kind of like the live stakes, lay it out, then tie it down with erosion control mat or with some level of biodegradable twine. Bury that in soil, seed it over. Maybe, if you know that you have additional pressures, put in a little bit of toe stone and then allow it to grow. In this project, that growth difference is 1 year. That was installation, come back next summer, and this is what we're looking at with regards to the growth. Again, will we get the same effects? Also, do we need to modify it? Do we want ice forming at the foot? Do we want a protective layer of ice? Do we want to keep it ice-free? Do we put in a series of boulders in front at different spacings to change the hydraulics? Because we know where frazzle ice develops, where anchor ice develops. Understanding what needs to be done with regards to the rock placement is something that still probably needs to be studied. We understand flow around vegetation. We understand flow under ice. Actually, Corinne Smith worked on her master's on the hydraulics of flowing water under ice. Interestingly, she is from Whitehorse. She did that research in Ontario. So, and then came back home because I think she missed the winters. And basically, so we understand those, but we don't know the interaction between them. There hasn't been a lot of work been done on the effect of vegetation and ice at the same time. Root wads. Benoit and I he had a really great point yesterday. We met for a coffee, and one of the things he pointed out is wood rots slower in the Yukon than it does in BC or Ontario. The use of wood in bioengineering might avoid one of the problems that we have in our own jurisdiction, was the fact that we have to pick specific species that are rot resistant. You may not have the same problems. I don't know if that is the case, but it arguably could be the case because of the colder climate. Again, root wads are basically wood mass buried into the bank. Maybe some rock is applied to the toe, and then it is buried and then revegetated in a lot of cases with live stakes, erosion control mat. My question is, how well will this hold up to an environment where ice is one of the main processes? Again, it's being applied. I know that there are locations where root wads are being installed. I know that talking to Daryl Cam at DC Environmental, and if I got that wrong, I apologize, because I talked to him for 5 minutes in Toronto Pearson Airport, and he told me that in the placer mining projects, they're using bioengineering. They're already installing things like root wads. So there is some surrogates, some locations where that could be studied to see what the impact of ice is. Vegetated rock buttresses. Again, these are materials are hydraulically sized. The vegetation is put in layering. This is what we're using in a lot of cases for erosion protection of infrastructure. It is a hard but green approach to bioengineering, and it provides benefits. But again, do we have to change the stone arrangements? How do we want the ice to interact with the rock and the vegetation treatment? There's an apology to the ecologists in the crowd. I've grabbed a couple of random species that are here. The palette may be smaller for bioengineering, but it is here. There's willow species, they're cold tolerant, they have rapid rooting, regenerate following ice damage. There's alders, suited for nutrient poor soils, established on sandy banks, rapid growth, and dogwoods. So all the materials that are required for the bioengineering are native and grow here. But there is a shorter growing season. The light blue is Whitehorse in the Yukon. I did not pick these randomly. I've done work in Brandon, Manitoba, which has a similar growing period. You can see this is just for the 1 year, 2025, or might have been average. Anyways, the growing season is shorter in Whitehorse, but there's other jurisdictions like Timmins and Brandon where they have similar growing periods and similar temperatures. Slightly different. It is colder here, but I will point out that Timmins is quite north. and it has a similar growing season, similar climatic condition, and we've done work there doing bioengineering, and in Brandon, Manitoba. I've done work there previously. It was installed and then immediately hit with a 400-year event. I am proud to say it was still there afterwards. Ice formation in the Yukon. I want to point out it does occur in other places. This is Bronte Creek. You can see the jumble ice trapping all the sediment. Here is the Yukon River, again with jumble ice holding all that material. There may be opportunities for reducing some of the sediment load and erosion by bringing plant material back into the system. We have ice on our floodplains. This is a great ice scar from all the jamming. I wanted to just point out that we are working with some of the same processes, just in a different level. Similar geomorphological processes, undercutting, expansion scour at culverts. We undersize our culverts too. Slumping, ice and hydraulic scour, just different measures of it. Freeze thaw, freshet and storm-driven hydrology, like atmospheric rivers coming through, which now impact some parts of Yukon and northern BC and bring a new peak into rain that isn't just related to the snowmelt. Ice occurs in both regions. The main difference lies in the length and the severity of the cold season and the dominance of ice processes in this jurisdiction. We have the same erosion problems. This is from Yukon, one of the Yukon rivers, and this is the approximate rooting depth. All the scour and erosion is occurring here. So all the energy is being exerted on an area where the material can be eroded probably between 0.5 meters per second and about 1 meter per second. If you were to lower that bank and include willow treatments, you could increase that to almost 3 meters per second, that it'll be able to resist erosion. In which case you're able to deal with this erosion in this area in a very similar way that it would have been done in Ontario. How do I know that? This is the Pine River. You can see me standing by this bank. That's the rooting depth. Put in root wads, terrace. That's what that blue line indicates, is a terrace to allow the water to get over, but more importantly, to allow the rooting depth to get to a point where it's protecting the bank. I put this in because we do the same thing with our culverts. We have the same erosion issues, as you can see with the protection up here, but again, your rivers are prettier. Pros of bioengineering in the north, the use of abundant local materials. We have a lot of nurseries supplying bioengineering materials. You have many point bars with a lot of alder and willows on them. Flexible and adaptable designs. Low disturbance installment, which means that you can do this maybe with hand labor. There may be some benefits, more benefits in the Yukon than in a number of the provinces. You have farther distances to go. If you don't have to take materials with you, or you can source some of the materials locally, it's probably a benefit. Ecological and cultural values, climate adaptation, alignment with Yukon's guidance, and in many cases, permitting with the Department of Fisheries and Ocean, and mitigation of ice-driven erosion. I think this is one of those areas that we really need to do some research on, is to look at that interaction between ice and bioengineering. Cons and constraints. You notice I'm waving my arms a little bit at this point because it was a talk about doing research and what we could do. The cons or constraints, limited species palette. There is less diversity in the species here, but there are species that can be used. Slow establishment. I think this is one of those things that really has to be examined. How long do you have to monitor? How long do you have to wait for it to be able to get the most benefit from the bioengineering? Requires maintenance. You need to do some monitoring. You need to do some infilling. But every time we manage a river, even if it's with an engineered solution, there should be monitoring because you need to know if it holds. Maybe it's not ideal for high-risk sites. Maybe it's used as part of a toolbox, but in very complicated or risk-intolerant sites, it might not be applicable. Vegetation and ice dynamics, I keep coming back to that, and vulnerability to river ice. Those are things that need to be examined, but there are areas with ice processes where bioengineering is working, and it's working effectively. Potential design adjustments, ideas and concepts, ice management and protection, extended monitoring periods. We usually go 2 to 3 years, maybe 5. Maybe you're going out to 10, maybe it's shorter, but it all depends on the growing cycle. Enhanced toe protection and rock armoring. Larger safeties factors of safety. Do you need a larger factor of safety because of ice rafting or ice scour? I'm not quite sure about the answer to that, but I know from our own jurisdiction, we use about a 1.5 factor of safety on the sizing, and it appears to work. Strategic vegetation placement, flexible vegetation, using things that will actually bend with ice. Bend, maybe break, but not actually take out the treatment with it. Use of pre-rooted materials. Maybe you're going to have nurseries where there's stocked materials there. Material sourcing. I think this is going to be a big one because of the distances that have to be traveled to do the work. You likely want to find locally sourced materials, or know that you have local providers that are going to be able to get the materials there, and just the availability of the native species. So my conclusions: bioengineering is successful and widely used as a form of erosion control in many regions across Canada, and it is being applied in the Yukon. Offers a flexible and resilient approach to erosion control over pure engineered methods. There are opportunities for ongoing research to optimize techniques for the unique climate conditions and process. That's my selling pitch. I would love to do research up here with regards to bioengineering, and I think there's a lot of opportunities. There's likely design adjustments that are going to be required. The same, but different. You can't simply take the detail, take the spec. You have to consider the processes that are dominant in your environment. And there is an opportunity to move from unique application, not just using it for habitat restoration, but actually applying it more widespread to using it as part of the overall toolbox for erosion control. With that, I want to make one request. I love the history of bioengineering. If there are any members of the First Nation community that know of areas of bioengineering may have been applied pre-European settlement, I would love to hear those stories that people are willing to share, because I try to collect records of where people have done bioengineering, because I know it's been used over and over again as a solution for erosion control and for many other reasons. And with that, I thank everyone for their time and questions. No?
So thank you, Paul. We have to be out of this room in 5 minutes, but I would love to give the microphone. I think there's floating microphones around. If you want to raise your hand if you have a question for Paul. I have a question in the back there.
I was wondering if you could go back to one of your slides on the river erosion, Yukon river erosion slide.
Which?
Back. Right there.
Yes.
That slide there. So that, excuse me for not knowing, estimation of lengths without an actual ruler. But let's say that's 100 feet.
Yep.
And then why is that
Why did
30 feet on the end there not eroded like the first 100 feet?
Great.
And
That's a great question. Part of the reason is this is actually probably on an outside, that's probably on an outside bend of a meander where you're getting a lot of pressure on the bank. But the other thing you'll notice is the floodplain is more accessible. So the rooting depth is lower down, which means that this area is generally being better protected by the existing and native vegetation, which is just a great example of how the vegetation can actually help to limit the potential erosion.
in the Yukon here, we have all these bends and flows in the rivers, and we see a lot of this erosion. I might actually, I tend to think it's the actual ground that's underneath it. Like, I would assume there's more soil on that last 30% than this 100% in the front is gravel based. Not, also considering the height elevation, but one of our biggest erosion factors, other than maybe ice on the river, is wildfires, just burning down a whole landscape. And how deep does that fire burn
I think a lot
into
of
the root system?
when you end up with fires, you end up losing the natural ability for the trees to intercept, and you lose a lot of the cover. It's not as much about losing the rooting depth, but it causes a lot of exposure to the soil. In this case, this area, and I have not been here. Corinne Smith actually took this photo, but when I looked at the image, that one is lower down. You're probably right. There's probably a thicker soil horizon, and there's just more rooting density in there to basically protect the bank. I'm also not advocating to stop all erosion. Erosion is a natural process that helps rivers form, but where we need to manage rivers or there's interaction with infrastructure, you likely do need some level of maintenance of the river system. Hopefully that answered the question.
Thank you, Paul. So I apologize. I know it can generate a lot of conversations, all that. Paul, you're registered for this event, so you'll be around this week.
I am here today. I'm also happy to talk to anyone who wants to ask questions out in the hallway once we are kicked out. If you didn't tell, I love talking about this stuff. So,
okay. Thank you so much, Paul. And thank you to everyone for coming for lunch today, and wishing you a great end of the symposium for those who are registered for the GeoScience Symposium. Thank you.